The topic I like to talk about today is the effect of starter fertilizer on performance of corn and sunflower as two crops which are supposed to respond to starter fertilizer the most. And it's very much the question about does it contribute to yield? Does it contribute to tolerance or resistance to abiotic stress? And finally, yield. And I hope I can highlight some topics here, some items which can answer this question and makes people in the field more capable to decide where to apply, where it makes sense to apply a starter fertilizer, and maybe where we can save this kind of cost and time to do it. So today, I like to start with the kind of underlying principles of starter fertilizer and the effects. So touching on the objectives, what we really like to achieve with starter fertilizer applications, the modes of starter fertilizer application, and after that, I will pause for some questions regarding the underlying principles of using starter fertilizers. And in the second part of my presentation today, I will talk about the application of starter fertilizer and results from trials in corn and sunflower to look at the yield response and maybe some other effects of using starter fertilizers. So, and finally, of course, I'd like to summarize with some key messages. So when we look at the objectives of starter fertilizer, those are quite obvious. Anyway, it's really to give the crop a push and to promote growth at the early growth stage immediately after seeding. And this should contribute to a faster establishment of the crop. So the crop can settle better in the soil. And if the crop is better settled in the soil, then we expect that it has a better resistance to soil-borne diseases, which can, of course, affect the crops at a very early stage already. With quite often a weak tissue with not very strong cell walls, etc. And also we expect that if we have cold weather, for instance, early during the crop establishment, that the crop can better tolerate this abiotic stress. Further on, of course, we expect an accelerated early development of the crop. So we speed up the growing process. And the focus at the early stage is very much a better root growth. And the better root growth contributes not only to, let's say, the root growth as such, it also contributes, of course, to a better and faster development of the shoot, as we will see later on. As soon as the shoot develops in a way, and then the crop develops leaves and so on, we expect that the crop stand covers the soil very soon. And by covering the soil, we know that we can reduce evaporation, means water loss from the soil surface. And by doing so, we expect higher water use efficiency by using starter fertilizer. In a way, by saving some water, but also, and this is also very important, the biomass production earlier is at lower transpiration cost, so to say. So per unit of dry matter developed, the crop consumes less water under, let's say, colder temperatures compared to warmer temperatures. And if we can accelerate the growth and development early, biomass production at the early stage is more water efficient. Of course, and that's obvious with better root growth and particular deeper root growth, the crop can access water in deeper layers later on. And also that could help to produce a higher or a more reliable yield under conditions where we have some stress situations during the growing season. And the picture on the right-hand side shows you a kind of very impressive effect of in-furrow, or meaning pop-up starter fertilizer, SDAP, compared to no starter fertilizer or no pea fertilizer into the seed bed. And we all know that when we talk about starter fertilizer, the first nutrient we think of is phosphorus because of, let's say, some very special soil chemistry and metabolism of phosphorus when it comes to phosphorus uptake. So the question is, of course, when we talk about starter fertilizer, we know about phosphorus is important, but why is it important, and maybe what other nutrients are important to have in a starter fertilizer to get the objectives we have, you will see on the left-hand side. The question about which nutrients are important is very much answered by their transport to the root and the efficacy of the root to take the nutrients. You are probably well aware that we have basically three, let's say, principles of nutrient transport to the root. The first one is mass flow, where the nutrients which are dissolved in the soil solution are transported to the root surface with the water. That's what we call mass flow. Quite substantial amount of nitrogen, potassium, calcium, for instance, also are transported to the root by mass flow and can be taken up, let's say, from the soil solution. The second, and the mass flow affects a distance from the root, which is in the order of magnitude of centimeters. I think the crop will take nutrients from, let's say, the root cylinder of about 4 to 6 centimeters around the root. The other principle is diffusion. Diffusion means that by a gradient of concentration of nutrients, the nutrient move via the water phase to the root surface. This happens only in the vicinity of the root of, let's say, 2 to 4 millimeters. And the last one is what we call interception. That means the root has to grow towards the nutrient source on a clay mineral or somewhere else, and can take it from there. When it comes to quantities, you can imagine that mass flow, we get a lot of nutrients to the root surface. Diffusion is of course less, and depends very much on the gradient of nutrient content or nutrient concentration between root and soil. And interception is quite often very, very limited when it comes to the total volume. When we look at all the nutrients we have to feed the crop properly, you see that different nutrients have different pathways of transport to the root, has different contribution for the different nutrients. So the green bar will show you the mass flow part, the yellow one is the diffusion, and the orange is the root interception. So, as I said, for nitrogen, sulfur, calcium, magnesium, They are transported by mass flow, and we wouldn't expect too much. Also boron, we wouldn't expect too much effect from these nutrients in a starter fertilizer, because normally they are a good supply when the crop takes up water. The critical nutrients are those where the majority is transported to the root and finally taken up as diffusion. And as I mentioned already, phosphorus, I think the biggest share of phosphorus uptake comes from the diffusion process. But next to that, we have the micronutrients, and here to name a few, I think when we talk about micronutrients and starter fertilizers, the focus should be on zinc and manganese, and maybe copper to some extent, but quite often it's it's limited to manganese and zinc. So yeah, when it comes to the nutrients in a starter fertilizer, we need to focus on those transported by diffusion mainly. And as I said, the focus should be very much on phosphorus, zinc, and manganese. Just to illustrate this a bit further, we have these two graphs here showing two different, or giving two different, or two messages basically. And the first one I have mentioned already, the phosphorus uptake is in the vicinity of 1 to 2 millimeters next to the root surface. And then the second one shows how temperature sensitive the phosphorus uptake is. So you see here in this graph, the phosphorus in the soil solution in the distance from the root surface in millimeters. So you have to imagine that the root is here at the, let's say, the 0 point. And then, of course, the root is able to deplete the soil solution, let's say, up to 1.5 millimeters. But you can see that in a bigger distance than, let's say, 1.5 millimeters, the root cannot exploit the phosphorus anymore. So only the phosphorus very close to the root is available to the root. And of course, if we have early in the season a very tiny root in the soil, of course, all the phosphorus which is in the soil, it cannot be accessed by this root, and therefore phosphorus supply by a starter fertilizer can help really to increase the phosphorus uptake of this kind of initially small root quite significantly. It's not only the distance from root, it's also that phosphorus uptake is more temperature sensitive compared to other nutrients. And on the graph on the right side, you see the iron uptake per unit of fresh weight. And the iron is the potassium and phosphorus, and the uptake is shown in dependence of the temperature. So what we quite often have, for instance, in corn, a soil temperature which is, at planting should be at least 12 centigrades. But you can see at 12 centigrades, the phosphorus uptake compared to the potassium uptake is much less. And this is mainly because the phosphorus uptake has a higher dependency on energy. And of course, we know that, for instance, the corn crop suffers from growing, meaning in a way providing energy to the different metabolic processes under cold temperatures. And to help the crop there, also phosphorus and a kind of concentrated high supply of phosphorus in a starter fertilizer can make quite some difference. It's not only the temperature, it's also moisture stress, which impairs the phosphorus uptake, or let's say transport to the root. And this is shown in this graph, because moisture means there are pores filled with water. And of course, the drier soil get, the less pores are filled with water. And for diffusion, availability of water is very important. So if the soil gets dry, less phosphorus can be transported to the root, and that means also less phosphorus is taken up. So on the graph on the right-hand side shows you the uptake of phosphorus in dependency of the soil moisture. So we have increasing, let's say, water stress on the x-axis, and you can see that phosphorus uptake responds to a water stress or reduction of soil moisture quite significantly. And the uptake, when we have a low level of phosphorus, of course, it's significantly less compared to a high level. But you can see that moisture stress can be overcome with high phosphorus supply. So let's look at medium. If you have a medium phosphorus supply and high water stress, the crop is still capable to take almost the same amount of phosphorus up compared to, let's say, a low phosphorus supply where we have hardly any kind of water stress. And the same applies, of course, for a high level. In a way, if you have a very high level of phosphorus, even on the, let's say, very limited soil moisture, the crop is still possible able to take up quite substantial amounts of phosphorus. So that means, you know, the concentrated starter kind of fertilizer can help under both conditions, low temperatures, but also limited moisture, to get at least the phosphorus nutrition right in the crop. When it comes to the, and this is really to show the effect of phosphorus application on root growth. And root growth is definitely, and in particular root length is definitely the property of a crop which reacts first to the phosphorus supply, and then of a kind of consequence of better root growth, we will see also better shoot growth. You see on in the graphs on the top, on the left-hand side, the total root length, and on the right-hand side, the length of the fine roots, and different levels of phosphorus were investigated. So in the bulk soil, we had a P deficiency, moderate deficiency, or an adequate supply in the bulk soil. And on top of this, baseline phosphorus supply in the soil, this graph shows you the additional effect of the localized phosphorus or starter fertilizer right at the beginning, applied right at the beginning, and the results shown here are 45 days after seeding, so to say, or 45 days after treatment. As we all know, a good phosphorus supply, and when the white bars here contributes to root growth, and we will get a significant response to overall good phosphorus supply. But with a localized phosphorus supply, a starter fertilizer, we can increase the root length even further, and this surprisingly applies, let's say, to this more or less the same extent for P deficient soils compared to adequate phosphorus supply in the soil. So to conclude on that, I would say, in a way, it's more or less independent from the phosphorus soil index, whether we will get effect from a phosphorus starter fertilizer in terms of root length, and also this applies to more or less the same extent to, let's say, the fine roots. It's not much different. This is not a maize crop, the picture with the roots, but where you see that the response to the different phosphorus soil indexes and indices and the localized, the additional localized phosphorus apply on root growth. And it's quite obvious that what the graphs show on top, and really also happens in the soil. So you can imagine that root system like we have on the left-hand side, right-hand side, sorry, in a way has the best capability to take nutrients and also the water from the soil and can support the growth to the maximum potential. But as I already have mentioned, now root growth is interesting for water and nutrient uptake, but also root growth, root branching contributes to changing the phytohormonal status of the crop. As you probably know, cytokinins, that hormone which is responsible for cell division, in a way is formed in the leaf, in the root tips, and then translocated into the shoots. And in a way, in general, the more new root growth we have, the more cytokinins are in the crop. And of course, the more is the shoot growth supported. And this is basically the reason also for a kind of accelerated development, as we will see in the next graph, next slide. This might be a bit complicated, but I hope you can follow when I explain it. So it shows you, how phosphorus startup or phosphorus supply, meaning in a way starter fertilizer or good phosphorus status in the soil, accelerates the development of maize. And basically we have the three lines represent three different phosphorus supply conditions. So the control without or with limited supply of phosphorus, and we have 45 milligrams of phosphorus in the soil, and then the 300 milligrams would be in a way what the roots will see when it get access to a starter fertilizer, kind of depot of phosphorus, very concentrated. And on the y-axis, we have the shoot dry matter accumulate weight over a period of time of 1 month after a crop emergence. You're probably very much familiar with the different growth stages in corn. So the trial has followed until the V6 stage. And as you can see, we have, of course, a response in dry matter accumulation. So the highest phosphorus supply contributes the most to dry matter accumulation to crop growth. And then, of course, we have the intermediate and the control, which are in a way has the least dry matter accumulation. But it's not only this. When we look at the time when a certain growth stage was arrived at, we will see that a well-supplied crop with phosphorus, for instance, reach, for instance, the V6 6-leaf stage, basically about 4 to 5 days earlier compared to a poor to a situation where we have a limited phosphorus supply, and this applies also for earlier growth stages. So that's, of course, something we like to see when we watch a crop in the field, that the crop develops fast. But the reason why it can contribute to a better yield is that by more accelerated development, faster growth, basically, we have a crop which somehow can escape from water stress, because this dry matter is produced under colder temperatures, and under colder temperatures, it takes less water to produce 1 unit of biomass compared to, let's say, what we have now. Even though the maize grows very nicely now, and it's almost like asparagus, but it takes much more water per unit of dry matter produced. And if we can, in a way, get this dry matter produced earlier, it saves basically water for later growing stages. Of course, a faster early development will contribute to an earlier row closure, so the crop covers the soil earlier, and the coverage of soil contribute to a reduction of evaporation. So the evaporation in the season depends very much on the area of shaded soil. In this case, it's a wheat crop, but it applies also for a maize crop. So if we have these temperatures today and we have still open soil, we will lose much more water by evaporation from a crop compared to from the soil, basically, compared to a situation where we have in a way the rows closed already, the soil shaded. And of course, the temperature doesn't increase and that so much at the soil surface, and that contributes to less evaporation. This is again shown in this slide. So, as we know, the transpiration efficiency in a way decreases with temperature, basically. So and the temperature here means in a way we lose a lot of water from evaporation from a pen in this case. So what we have in let's say April is much less compared to what we have later in the season, because in a way the water deficit in the air because of temperature is much lower under colder temperatures. And what I said, in a way, if we accelerate the growth of a crop early in the season, then we can shift the biomass production to earlier days, and this means also we have a higher efficiency, water use efficiency, compared to an array crop which has a kind of delay in development. And overall, in a way, early development, because of this underlying principle, results in higher water use efficiency. And this is definitely something which is very important when we look at starter fertilizer. But let's say for the next couple of slides, it's very important to understand what we understand as a starter fertilizer and what kind of different modes of starter fertilizers are available and used in agriculture. And this is shown in this slide, where we have the application modes of starter fertilizer. Basically, we talk about 3 different ones. I think there's a 4th one, and I will come to that in the next slide, which is seed coating, can be also considered as a starter fertilizer. Of course, as we know, that with the potential of very limited quantities of nutrients, but of course for some micronutrients it can be quite, it can have a quite significant effect. What we normally do in maize is more or less standard practice in corn, and maybe also in other crops, is the placement 5 centimeter next to the seed and 5 centimeter underneath of the seed. This is what we call fertilizer, underground fertilizer placement. in some areas we have a similar system, but the starter fertilizer is just dribbled or applied close to the seed row, next to the seed row, but to the soil surface. Not so much used in Europe, but we have some in US, and quite often they compare this one with the placement when we look at trials. And then we have something we call pop-up in a seed row, or in the seed furrow even. That means the seed and the fertilizer and the way sits very, very close to each other. And of course, for pop-up fertilizer, we need to be very careful, because all fertilizer expose some, let's say, salt stress. And if we exceed kind of critical limit there, then of course the germination and so on is impaired, which needs to be avoided as much as possible. And for this reason, the quantities we can apply as a pop-up or in furrow, or what we microgranule starter fertilizer, as it is used quite often, is we have only the opportunity to apply limited rates. Normally we talk about let's say not more than 20 kilograms product per hectare, to avoid this salt stress as possible, as much as possible. When it comes to the placement, I think the salt stress is avoided to a largest extent in a way by having the distance between the seed or germinating seed and the fertilizer. So basically, with this kind of application, much higher rates can be applied compared to pop-up application. And when it comes to the restrictions to what kind of fertilizer material can be used there, if it's if it stays in reasonable amounts, then there's hardly any restriction on what can be applied there, if anyway the placement is done in a proper way. For pop-up, yeah, as I said, it's applied very close to the seed or in the seed row. We quite often see good phosphorus response. What needs to avoid it is those products which can really impair germination quite significantly, even at low quantities. Urea, boron, we need to be very careful. Ammonium thiosulfate, those in a way shouldn't be considered really as pop-up fertilizers. And it has limitations because of the salt stress we expose with almost every fertilizer, every nutrient. But it applies to a very large extent to nitrogen and potassium fertilizer, because they are almost 100% water soluble. That means they expose the highest salt stress in the soil, and therefore depending on row spacing, we should watch some limitations for applying these two nutrients in total. For instance, if we have a row spacing like in corn, 75 centimeters, not more than 10 kilograms of these two nutrients should be applied per hectare. And in a sandy soil, which has even a lower buffer capacity, lower water holding capacity, it should not be more than 7.5 kilograms per hectare. And so as soon as the row space increases, of course, you can go a bit higher because you have kind of longer row for the same amount of fertilizer applied. If it becomes wider, then even the limitations are less. As I said, there is a fourth one, which is seed coating, which is I think common, and I think there are more and more seeds coated with micronutrients in particular, because sometimes it comes with some phosphorus, but the amount of phosphorus you can add with the seed coating is quite limited, can help maybe for a couple of days. But you know, for micronutrients, the quantities are by far lower compared to the other nutrients, and with seed coating we can add on quite substantial amounts of micronutrients. And then the question is, what can the micronutrients do on corn seeds when it comes to root and shoot growth? And in this graph, it shows the root length and shoot length in centimeters. This is from a lab trial. And then they use the same kind of product in a field trial, and then the grain yield has been measured. The two nutrients used there were boron and zinc, and it was the control without seed coating. Let's look at the boron first. In terms of root growth, you can see that both root and shoot length has declined by boron applied to the seed. And in conclusion, we have to say that boron seed coating is kind of risky and probably will be not very common because it has this effect on the early development of the roots, and then not further on shoots. So it impairs, at least temporarily, the growth of root and shoot. The zinc coating is different. You see different quantities here, 1, 2, 4, 8 grams per single sulfate per kilogram of seed. And you can see that in particular, the root length compared to the control here has been increased quite significantly. Not so much the shoot growth. And again, the combination of both, we have the limitation by the boron, at least at these kind of quantities cannot be recommended. But zinc, for instance, we see has an effect on shoot growth. Later on, we see that we have also an effect on grain yield. So it looks like that this kind of impairment by the boron early has been compensated later in the growing season. So there were no reduction in yield, it was more the opposite. So late in the season, obviously the corn crop could benefit from the additional boron supply. We know that maize corn is a very demanding crop for boron. And under conditions where boron is maybe short in the soil, now this boron applied with the seed can contribute to increase in yield. In this case, it's even almost half a ton, which is quite substantial, I would say, but probably applies very much to conditions where boron is limited. And this effect shows up even though we know that maybe early it's not a good idea to have boron on the crop, and probably in a way on the seed, and probably this crop will look not very nice early compared to let's say treatments where we had zinc only. A very good response also to zinc. You can see with additional zinc supply, quite substantial yield increase in this trial. Again, it depends also on the zinc supply of the soil in general. In a way, I wouldn't say that you can expect this 1 to 1.5 ton at each kind of under all conditions, but I think if for instance, zinc supply is short, then seed coating can be definitely an option. Let's have a closer look then, in a way, what happens in a fertilizer depot. And this is shown in this graph. So we have the crop here, and then the the placement somewhere here. And quite often we observe the best effects of fertilizer if some nitrogen in the form of ammonium or also urea is present in the starter fertilizer. And the reason why is that the crop roots is attracted by high nitrogen concentration. So the nitrogen from a depot in a way diffuses into the soil. The crop root in a way sees it, finds the nitrogen and grows towards the nitrogen source. So it directs the roots towards the, let's say, the placement zone, and in the placement zone, in a way, it finds all the phosphorus and also maybe other nutrients which are in the starter fertilizer. So therefore, the ammonium form or urea form in a starter fertilizer creates a synergy between the phosphorus and other nutrients and makes the starter fertilizer more efficient. At the same time, the ammonium uptake contributes to a kind of acidification close to the root surface, and by acidification at the root surface, the micronutrients become more available, but also phosphorus become more available. And by having a very concentrated fertilizer depot, the precipitation or locking of phosphorus is avoided to a large extent. So the phosphorus stays in this depot very much as it has been applied in a quite often water-soluble or in a mixed form of water-soluble or non-water-soluble form. And the water-soluble form is, of course, very important for the diffusion, because you create a very high concentration here, which means, and a low concentration close to the roots. That means there's a high gradient, and a lot of phosphorus can be taken up from this depot. Before we pause, I'd like to share a bit findings from the meta study published in 2016, where a lot of trials have been reviewed, in total 770 trials. On average of these 770 trials, they found a 3.7% yield increase overall all crops. So this is basically what can be expected on average as a yield increase from starter fertilizer, taking all the trials into account. You can see that different crops respond differently. So we see on this graph, one means there was no response to starter fertilizer, applies to some of these crops. Of course, today, very much maize is in focus. And you can see a lot of trials have been done in this maize. Out of these 770 trials, we had more than 400 just in maize. Overall, we can see also kind of similar response, 3 to 4%. The response in potato, even though there are only 6 trials, seems to be quite significant. As we know, potato has a very kind of shallow poor root system. So this is also a prerequisite for getting a good response to starter fertilizer. I don't like to touch too much on the others. Unfortunately, there are no sunflower trials, so I cannot share anything there. The question is always, where the depot should be and what kind of nutrient form or nutrient has shown effects. Let's say this is very much a surface application. Again, liquid manure, I think it's not so much of interest now. Again, we will see that we get, of course, from potassium hardly any effect. As expected, ammonium and phosphate, quite good effects. And then depending on the placement depths, either 5 to 10 centimeters or bigger than 10 centimeters, I think is not surprisingly not a big difference there. again, ammonium and phosphorus, or urea and phosphorus. Those are the mixtures, let's say, in the fertilizer where we, in trials at least, got the highest response to. And this shows that starter fertilizer should consider the formulation of these nutrients quite a lot. When we look at the overall response to starter fertilizer, what can we expect? So the subsurface placement of fertilizer close to the seeds of plant roots can lead to higher nutrient uptake. We have seen that. A higher concentration of nutrients in the above ground biomass, and a higher yield than broadcast of fertilizers. The mode of action, as I played, is high levels of nutrients. They stay in the plant available form close to the roots. The stimulation of root growth and branching around fertilizer depots holding ammonium, urea, and phosphorus, or a combination, improve the exploitation of these nutrients from the soil, and the induction of favorable changes in chemical and biological processes of the rhizosphere. And by having these effects, in more intensive uptake of root, of course, we can reduce losses, in particular nitrogen losses as nitrate. So that means we can expect quite a lot, but of course, what we are interested in is what it does on our crops. And I like to start with corn as one of the most responsive crops towards starter fertilizer. There's a publication, a recent publication from 2020, where they have measured the effect of phosphorus placement on the phosphorus recovery and the agronomic efficiency of phosphorus use in corn. The trials, the average, the mean of, the results are the mean of 4 years, and they have measured in a way how much phosphorus applied by the starter fertilizer finally arrived in the crop, and what we call phosphorus recovery of the fertilizer in the crop in percentage, and to what extent each kilogram of phosphorus has contributed to dry matter production, meaning corn production, and that's what we call agronomic efficiency. The comparison was always a broadcast application of the same amount of phosphorus compared to what they call a banded or placed phosphorus, 5 centimeter deep, 10 centimeter deep, and 15 centimeter deep. You might be surprised about the low figures on the y-axis. So from the phosphorus applied, if it's broadcast, only 7% were really recovered in the crop, and by the placement, the recovery was quite substantially increased by about 11 by about 5%, which is quite substantial. And the most important here is that even though it's a low kind of quantity compared to what has been applied, this quantity is most effective early in the season when the crop has still a kind of poor root system where the phosphorus supply matters the most. Later on, as the crop, and the corn crop in particular, has developed the crown roots and everything, the roots go very deep. The phosphorus supply through the placement from the starter fertilizer is not so important anymore, because in the big root system can take the phosphorus anywhere in the soil, and that explains very much in a way the kind of low phosphorus recovery. Yeah, but it shows also that the placement in the depth of, let's say, 5 to 10 centimeters, in this case below soil surface, is the right way or the right recommendation to follow So the 5 by 5 means 5 under the seed. Now it meets, of course, this kind of soil depths. The mode of application and placement, as we normally do in Europe, is pretty much okay, and follows very much in a way findings from trial. The agronomic efficiency, just mirrors what is recovered early from the phosphorus starter fertilizer. So meaning when we have placement, the dry matter production per kilogram of phosphorus applied has increased quite substantially by 12 kilograms. So that's it's almost doubled the dry matter production per kilogram of phosphorus. That means our starter fertilizer banded in corn is a very, very efficient way and makes the phosphorus the phosphorus fertilizer very efficient. The question is, do we always need a band all across the seed row? And this has been investigated also by a recent trial where they compared a point source. So that means applying the fertilizer indicated here as green dots just only next to the seed. So the yellow dots are the seeds, the corn seeds. And they compared this mode of application with a band placement as we normally do. So that's a standard application. I think it has implications with the machinery. Of course, now a continuous kind of band placement is much easier than now I have technology to do a point source. But this trial in a way gives you some interesting insights to what matters when it comes to placement. It's only in a way really the vicinity of the fertilizer depot to the seed, and less so the total quantity of phosphorus, nitrogen, or whatever is in the fertilizer applied, because it matters only right at the beginning. And in a way, what's in the middle of these two seeds is less important compared to what it's close to the seeds, because it's the distance to what the fertilizer place here is higher. So really, distance matter as a result for sure. And how they did it is again shown here on this picture. You have the seeds, and then next 5 centimeter next to the seed and 5 centimeter underneath of the seed, the fertilizer depot, either as a point or as a band applied to the soil. And the results basically show that the point with a point source, you can even save product and get the same kind of yield response. Just to show a bit what kind of fertilizer has been used. There was a liquid fertilizer, a mixture here, because this liquid is probably easier to really apply it as a point application compared to let's say granular fertilizer. It was a fertilizer very high in phosphorus, had some potassium, some nitrogen, and then also some micronutrients, the full range of micronutrients chelated, even so kind of very high value product for sure. Yields were recorded after application as a point or as a band or belt for 3 years. And you like to focus just on the overall mean. So yields in this case were quite low. I think it comes from, let's say, the Central Asian country, but I think it still shows very nicely the principle, even so the yields are much lower compared to what we are used to. We have an effect to the starter fertilizer, so the control was just 3.4 tons, and it was increased by about half a ton in this case. with a starter fertilizer. And then the question was, how efficient is a point source compared to a belt? So they used only 35 liters of this product for point sourcing, point application, and 50 liters per belt application, or a higher rate was 70 compared to 100. So basically, the hypothesis was that they can save some 30% of fertilizer by point application. And the results reveal that this is the case. So you get almost the same yield effect with 30% less fertilizer applied as a point compared to the belt, both at let's say low and high rate of starter fertilizer. So just illustrate again how important the distance to the root is, and that fertilizer which is in a bigger distance, in a greater distance to the root, doesn't have the same starter effect compared to what we have, for instance, in a 5x5 pattern. When we look at the effects of starter fertilizers, we see some results from Europe, but I think starter fertilizer is even more under discussion, and the effects and value of starter fertilizer more under discussion in US. And therefore, in the next couple of slides, I'd like to share some results from the US, where different modes of starter application have been tested in terms of the early development in this slide, and also later on in terms of yield. So this is a trial done by the Purdue University, and this university has 3 different trial sites indicated with these acronyms here. And they have measured the percentage of plants which arrived at the tasseling or R1 stage after the application of different starter applications. They compare the control pop-up fertilizer, so it means fertilizer applied to the seed row, a low starter fertilizer, a combination of the pop-up and a low quantity of starter fertilizer, and a high starter fertilizer application, indicated by these different colors. So the quantities applied, again, it was liquid fertilizer. The pop-up was 3 kilograms of nitrogen and 10 kilograms of phosphate as ammonium polyphosphate, 1034, very common starter fertilizer in US. Then the low starter, they followed the 5x5 placement pattern. It was a liquid, but with, let's say, the same amount of nitrogen compared to the phosphorus, 1917. Total applied 31 kilograms of nitrogen, 28 kilograms of phosphate. And then the high starter was, they doubled the rate of starter. So arriving with the same product, arriving at 62 kilograms of nitrogen and 54 kilograms of P2O5 applied as a starter. And you can see that the effect on earliness or early crop development compared to the control was there for all kinds of treatments. So just for instance, here less than 3% were at tasseling stage at the time of observation, compared to 45% in the high starter application. And this is very much, this follows very much the same pattern on all these 3 sites. So we get a kind of significant earlier development of the crop with starter fertilizer. We also see that pop-up fertilizer has an effect, but it's kind of limited. The best results in terms of earliness we get from the high quantities, the blue bars, and some in this slide the combination was of pop-up fertilizer and low quantity of starter fertilizer has been the best. So if that what I have explained earlier, that in a way earliness matters for, let's say, better water use efficiency and so on, has a lot of effects. We would expect based on this, let's say, earlier development of starter fertilizers also a much better yield. And disappointingly, I would say, when we look at the yield response to starter fertilizer on the same sites in 2 years, 2014 and 2015, out of these 6 site years, we get a significant response in yield only on 2 sites. Means in a way 30% of the cases we get a response in yield also. And on the other sides, the starter effect hasn't contributed to a significant yield increase. This highlights very much that in a way, an early development in corn doesn't mean necessarily that we get a better yield, and this applies very much under conditions where the rest of the season anyway has only very few yield limiting expose very few yield limiting conditions, means water supply, extraordinary heat, and so on. If there are no limitations further in the season, the corn crop can compensate a delay in development early with a better growth later on. And this explains in a way why we not always see a better yield response to earliness and to basically to the effect of a starter fertilizer early. So basically, this means under conditions where we have situations in the season where maybe we have a drought later on, or we have in another season where we have good water supply, the starter fertilizer probably needs to be considered as a kind of insurance towards this kind of conditions where the corn crop cannot compensate the earliness or the better growth, or the worse growth when you have no starter later in the season, but it materializes if we have limitations of growth later in the season. So then we have better responses to the starter fertilizer. So it's not always given that we get a yield effect. This is also shown in other trials. This is also, let's say, a trial with a pop-up in-furrow starter on development and the yield of corn. I think 15 years of trials on one side in Louisiana, US, where they used again this liquid starter fertilizer and compared it with the liquid starter fertilizer, ammonium polyphosphate 1034, and then compared it with a starter fertilizer where they use only a nitrogen source, UN liquid, and the control, no starter. And as you can see here, the earliness is indicated as the plant height in inch. Over the time of let's say almost 1.5 months from, let's say, early development towards probably some, 6 leaf stage in US, And you can see that plant high is always ahead of with starter fertilizer is always ahead of the control, but also ahead of the only nitrogen only treatment. So there's no doubt that starter fertilizers accelerate growth early normally and on average. The question again is, how it contributes to yield, grain yield. You see the green bars are those treatments with the starter fertilizer, and the blue bars without starter fertilizers. Basically, we get always a kind of response. There's only one exception where in a way they were the same, or even without the starter fertilizer was even a higher yield. But when it comes to statistics, we see a statistically significant response in yield only in five years out of these 15 years, with a significant yield increase. And this can be sometimes quite substantial. In this case, for instance, 1995, probably summer was very dry later in the season. So the earliness has contributed to more than 1 ton extra yield. That's of course kind of extreme. Here's another significant response. So it's about half a ton to max 1 ton extra yield because of this starter fertilizer. So in general, I think over the years, this kind of nutrients is not kind of extra cost because it's considered in the overall nutrient budget. And so it's not a loss of nutrient, and it's an expense which has to be made anyway. And there's always the question whether the additional workload at planting in a way pays or in a way is can be justified by this additional yield increase or by this yield increase. And in general, I think still pop-up fertilizer or placement is still very popular. It's more in US. It's more or less a standard practice in many European countries, in particular northwestern European countries under, let's say, colder climate. And therefore, I think it can be definitely recommended to corn as an insurance. And sometimes, in a way, if something gets wrong later in the growing season, we will see also good responses in terms of yield increase. So this again shows a bit whether there is a difference in the response, in, let's say, depending on the tillage system in use, as a conventional plow-based system or reduced tillage system, and the response in yield, either in soils which has a low phosphorus soil index or a high phosphorus soil index. And they compare the control in a conventional tillage and reduced tillage with starter fertilizer, in this case 5x5 placement. And where the message basically here is that in these conditions that they have been in Minnesota, this is a 2 years average, it looks like that the yield effect in a high P soil was in these 2 years were kind of at the minimum. On a low soil index, P index soil, we had a small increase, but in a way the placement, the deep band placement, was the most efficient one. In reduced tillage, it seems to be that in particular in low P soils, we get a good response to starter fertilizers. Again, the deep banding the placement is much better than the broadcast or surface band applied fertilizer. So when we have systems which are probably, as I explained in the previous session, which has probably some shortages when it comes to warming the soil and so on, otherwise the starter fertilizer might be more important, and this applies to reduced and no tillage. I think that's also one reason why the placement starter fertilizer is still very common in US, because most of the corn there is planted in North America as, with a no or reduced tillage system. Let's look at starter fertilizer applied to sunflower. And I have to admit that there is not too much research and trial data available for sunflower. I think it's in sunflower placement or starter fertilizer is less popular and not so much in use compared to corn. The difference might be, and this is something I haven't mentioned yet, corn is a C4 crop, so it has a different kind of photosynthesis assimilation system compared to sunflower, and therefore sunflower is a C3 crop, and therefore probably corn is more sensitive to, let's say, unfavorable conditions like cold and drought compared to sunflower, and therefore we probably haven't seen so good effects of starter fertilizers in sunflowers compared to corn. And I have checked literature, at least in the Anglo-American kind of literature. There are not too many papers dealing with fertilizer placement, starter fertilizers in sunflower. The only one I found was one from the early 90s already, where they have tested different starter fertilizers and splitting of starter fertilizers with nitrogen top tracing in fields which were either rain-fed or irrigated. You can see easily in a way the treatments which were irrigated. They're very much on the left and right hand side. The bars there. Of course, with irrigation, we get the much higher seed yield in sunflower. And the comparison in irrigated treatment were that they applied phosphorus and 50% of the nitrogen broadcast at seeding, and they had a top dressing after the first irrigation. The direct comparison is, of course, the placement, the starter fertilizer applied with at seeding. So basically the same kind of split between the phosphorus and nitrogen. All the phosphorus were banded, and then 50% came with the starter fertilizer. The other 50% were top dressed after the first irrigation. And under those circumstances, the starter fertilizer has increased yield by 18%, quite substantially. In rain-fed system, we have basically the same comparison, but all the nitrogen and all the phosphorus were either applied at planting, broadcast, or banded. And you can see that under those conditions, the yield response to the starter fertilizer was quite substantial. So it was a yield increase of 33%. Unfortunately, this paper doesn't hold any information what kind of soil it was and what the overall phosphorus soil index was. But I guess this kind of yield increase we can expect if the soil is really, really very, very poor in phosphorus. And I think in a way it would be really a bit a shortcut to say, in a way, yeah, it makes a lot of sense to apply a starter fertilizer to sunflower. What we can say, it's of course it doesn't harm, and it can contribute to yield again, depending on limitations caused by growth conditions later on in the season. And it's a question of how much extra effort it is really to apply it at planting already compared to a broadcast application. But of course, if this kind of workload, if in a way the overall crop management and plan for the holding, is this time is available at seeding, I think it can be recommended to do in a way the fertilizer application. I think more or less the total phosphorus and nitrogen application at planting and as a placement. So when it comes to in a way pros and cons, strengths and weakness of phosphorus application modes, comparing of course the different starter modes of starter application with broadcast. The strengths definitely we have this early growth, and this can increase the yield if soil tests are low. Most effective will be pop-up fertilizers if it includes some micronutrients, because most of the time those can do a better, even a better job than the phosphorus or some nitrogen only. I mentioned here boron, but we need to be careful with the quantity of boron. Should be very, very limited, because otherwise maybe you get a kind of impairment of the early establishment. And this is of course a weakness. If we get it wrong, there is a risk that we reduce germination. There is extra equipment in the plant to carry the pop-up fertilizer, and additional phosphorus fertilizer needs to be applied anyway to meet the recommended rate. Okay, I know that can be done sometime in the crop rotation and doesn't need to be to the maize crop necessarily. But basically, we have, there is the likelihood that we have to apply another fertilizer to get the phosphorus rate. The placement can increase yield in a high yield environment. It's most effective if soil phosphorus levels are low to medium level. The band should be placed 5 centimeter next and below the seed. And it is most effective in combination with ammonium, and it increases phosphorus uptake efficiency. It may not so effective for low yield potentials, and maybe not practical for high phosphorus rates, because the amount of fertilizer you need to be applied at planting is it's a lot of effort to put into the planter and so on. So additional fertilizer have to be applied if this is the case. So extra equipment and time to carry the product as a fertilizer to the field and to apply is also a weakness. But of course, if under conditions where we can apply all the phosphorus with this with a starter fertilizer, this might be not a weakness anymore. The pros for broadcast: it's easily applied. It not only increases the phosphorus level in a small part of the soil, normally it's incorporated, so it increases the level in the bulk soil, and it could be more effective than placement if there is a very high demand for phosphorus. So in US, they work with, if they need to apply more than 50 kilograms of phosphate per hectare, then maybe it's better to have it as a kind of broadcast application. It might be less effective than placement for low phosphorus rates, and maybe less effective than soil P levels are very low, because then you need to build the phosphorus level in the soil, and this can be done also. And you need to increase the phosphorus concentration in a small piece of soil, so that the phosphorus applied is more efficient compared to a just broadcast application. Is it recommendable or not? Yeah, I like to conclude the following. All starter fertilizer application, be it seed coating, pop-up, and placement, they contribute definitely temporary, at least, to an improvement of nutrient supply and nutrient uptake. Crops respond mainly with an accelerated early development and growth to starter phosphorus and micronutrients. Synergies derive from the combination with ammonium, and therefore these kind of combinations are recommendable. We have to watch maximum rates for starter fertilizer, which is applied into the farrow, what we call also pop-up fertilizer, because of the risk of soil damage during germination and early establishment. Seed coating is most effective for micronutrients. Small quantities can help, and close to the seed, the efficiency is, can be quite good. Pop-up applications or in furrow microgranules are most effective if no further phosphorus is required. So means you need to boost the early supply, but then the soil is very high, and phosphorus doesn't need any additional quantities. The placement 5x5 is recommended in regions where low temperatures impair establishment of the crop, and if all phosphorus recommended phosphorus can be applied with the placement already. It looks like that no-till managed crops seem to be more responsive to starter fertilizer as a placement. That has to do with the soil conditions, temperature at the soil surface, which might be lower under no-till conditions where we have a lot of residues on top. Starter fertilizer are most effective in corn because low temperatures impair phosphorus uptake, probably more than it does in other crops like sunflower. Starter fertilizer effects in sunflower are less likely and therefore not so common to use it. But as I said, if all the phosphorus can be applied and if the workload at planting allows to do a placement, I think it's also recommendable, because it doesn't do any harm, and there is an upside that under certain conditions also we get a yield response. I think so far is what I can conclude on the trials I have seen, and also based on my experience with different starter fertilizers. And I leave it for discussions and questions, and maybe also to see in a way what you consider to apply in Ukraine, and how you work with starter fertilizer in Ukraine.